Hey guys, welcome to Safi Mixed. In this video, I'm talking about well-defined observables. So I would like to begin with the definition of such observables. A well-defined observable is one for which the uncertainty in its measurement is zero. And we know that in quantum mechanics, observables are represented through operators. So an observable that correspond to operator Q is said to be well defined if the uncertainty in the measurement of the operator is zero, that is, if delta Q equals zero, where delta stands for uncertainty. So if delta Q equals zero, that means the uncertainty in the observable is zero. And we also know that uncertainty in the measurement of a physical quantity is mathematically given by delta Q equals square root of average of the square of the operator minus square of the average of the operator. So if delta Q equals zero, then equation 2 straight away leads to average of the square of the operator equals to the square of the average of operator. So from here we can say that a well-defined observable is one for which equation 3 holds. The left side of equation 3 is the expectation value of the square of the operator Q, and the right side is the square of expectation value of operator Q. So when the expectation value of the square of an operator is equal to the square of its expectation value, it is called well-defined observable. Now let us see when can equation 3 hold true for an observable. To this end, I follow the normal procedure for finding the expectation value of operators. That is, we know that the expectation value of an operator is measured with respect to a wave function. Let the wave function be such that Q applied to the wave function reproduce the same wave function with a multiplicative factor, which I write here as a small q on the right side of the equation. When this equation exists, then the small q on the right side is called the eigenvalue and the wave function is called the eigenfunction, and the equation is called eigenvalue equation for the operator q. So equation 4 is in fact an eigenvalue equation. Now let us use the defining equation of expectation value and find the expectation value of the square of the wave function. So by definition, I can write the expectation value of the square of operator Q equals integral over the whole space psi steric Q square times psi integrated over the whole space dV, where dV of course stands for the fractional volume and integrated over the whole space. Now I can rewrite this equation in the form integral over V psi steric Q, and then I'm putting brackets, and inside the bracket I'm writing again Q times psi. Now using the definition of the eigenvalue equation, I can write Q applied to psi equals small q psi, and can rewrite the equation into this one form. Since small q is a number, therefore I can change its position with respect both to operators and psi steric, and therefore I take that out of the integral and can rewrite this part of the equation as small q times integral over the whole space psi steric q times psi dV. And once more, using the eigenvalue equation for q, I can rewrite this as small q integral over the whole space psi steric small q times psi, and once again taking the small q to the left side of the integral and multiplying with the other small q, I can set that equal to square of q and can rewrite the equation as q square integral over psi steric psi dv. And psi steric psi is in fact the modulus square of psi integrated over the whole space is in fact equal to 1, which gives a normalization condition, and I can put the result in the form equal to q square, and small q square is in fact the square of the expectation value of operator q. Therefore, I finally put the equation into this form, that is the expectation value of the square on the left side of the equation equals the square of the expectation value, which is the right side of the equation. In fact, we have truth equation 3. Now, look, we obtain this result by using the eigenfunction of the operator. So, this means that any observable measured in any of its eigenfunctions is free from uncertainty and is therefore a well-defined observable. Thanks for watching.